Welcome everybody to my talk entitled Network Neuroscience and Machine Learning-Based Predictive Modeling to Understand the Brain Basis of Human Intelligence. At first, I would like to say that it is a great honor for me to be here, and thanks for inviting me to this summer school at this great location in this meeting here. As I'm not that familiar with your background, you can always disrupt me whenever you want. Yeah, just raise your hand and ask me questions. To provide you at first a brief overview, I will start with some general considerations about intelligence. Then we will enter the field of neuroscience first and see what neuroscientific investigations have identified as correlates of intelligence over the last decades, both with respect to brain function and with respect to brain structure. We will then continue with a more connectionistic perspective, which moves beyond the consideration of single brain regions and consider the brain as a complex network. Following this perspective, I will provide you insights into some of my ongoing and also into some planned projects of my research group, inclusively introducing our recently developed new machine learning framework that can be easily transferred to all other domains of individual differences research. So whenever you are interested in predicting individual differences in personality, in disease risk, also on, you can transfer our frameworks, and I'm always happy and open to collaborate with you in your research or your research groups. Then I will end with our discussion, and we will have a lot of time for open question in the end. So let's start. At first, although you introduced intelligence, I will introduce it a little bit again from a slightly different perspective. So what actually is intelligence? In general, although nearly everybody thinks that one might know what intelligence is, there exist many different scientific definitions. But some of these definitions stress similar concepts. And to get a brief impression, I will show you here a quite popular definition which was developed as common agreement from 52 established intelligence researchers in 1994, and which captures quite well my personal understanding of intelligence. So, intelligence is a very general mental capability that, among other things, involves the ability to reason, to plan, to solve problems, to think quickly, and to learn from experience. It's not merely book learning, a narrow academic skill, or test-taking smarts. Rather, it reflects a deeper and broader capability of comprehending our surroundings, catching on, making sense of things, and figuring out what to do. Today, there exist well-established tests to allow the computation of a so-called intelligence quotient. These scores are typically normally distributed, meaning that most people have a score around 100, and only very few people have very high scores or have very low scores. Such scores aim to capture the cognitive ability level of a person within a single value, and importantly have been shown to predict important life outcomes like socioeconomic status and occupational success. Therefore, the investigation of the biological basis, the fundamentals of intelligence, is a highly relevant research topic. Early studies found evidence for intelligence-related activation pattern in frontal and parietal brain regions. An observation that gave reason to propose the parietal-frontal integration theory in 2007. A more recent meta-analysis of our research group revised the PFID model then in 2015 and revealed the involvement of a more widely distributed set of brain regions, or let's say the involvement of a whole brain network. Importantly, these regions represent regions where variations in neural activation are associated with individual differences in intelligence. So these brain regions do not represent brain regions that are generally on a group level activated when solving complex tasks, but rather these brain regions in which are regions in which between person variations in activation, for example, are related to between person variations in intelligence. Okay? This is important to hold in mind because this refers to all I will present today. We are always interested in neural markers of individual differences in intelligence, not in cross-person effects. But not only neural activation has been linked to intelligence. What about brain structure? One of the most established findings is a positive association between brain size and intelligence. One can, of course, speculate about the underlying causes for this, but it indeed seems to be true that smarter brains are larger, for whatever reason. While former structural studies identified single regions associated with individual differences in intelligence, more current research suggests also here that structural characteristics of a whole brain network are important for intelligence. And here you can see the results of a meta-analysis from my research group where we compared all studies that reported differences in regional gray matter volume published until 2015. Overall, also this meta-analysis resulted in a widely distributed set of brain regions, and cross-study heterogeneity in the reported effects was very, very high. So also these findings serve support for the assumption that a whole brain approaches that consider the whole brain and do not focus on specific regions might be better suited for the purpose of detecting the structural underpinnings of variations in intelligence. So, and then following this whole brain perspective, we recently applied machine learning techniques to regional brain gray matter volume of 300 persons. The overarching aim of this study was to test whether we can predict individual intelligence scores from multivariate pattern of structural variations. In brief, we used support vector regression and implemented two different feature construction methods to finally observe that significant above chance prediction of individual intelligence scores from regional gray matter volume was indeed possible. However, important to note is that the mean absolute error was quite high, and around 10 IQ points. This means that on average we would make 10 IQ points error when predicting the relevance, when predicting individual intelligence scores, which questions a little bit the practical relevance of such predictions. However, we find it quite interesting that we at least can predict above chance so significant prediction. Furthermore, we showed that prediction accuracies decreases when controlling for variations in brain size, and that this prediction cannot be attributed to a specific brain region or a specific network. So we need the whole brain again. Building then upon these and other research findings, studies in the following years, inclusively my own work, started to take a more connectionistic perspective. They treated the brain explicitly as a complex network and aim to answer the question whether the neural basis of intelligence may potentially lay in a better organized brain network, in better organized connections. In general, brain connections can be structural, reflecting the right matter tracts in the brain, and are typically measured with diffusion tensor imaging, or they can be functional, where connections are modeled on the basis of statistical relationships between the time courses of neural activation from two distant regions called network nodes. So when two nodes are fluctuating in their neural activation pattern in the same oscillation pattern, then we assume that there is a functional link because they are on the same time activated and at the same time deactivated. All these connections that are also called edges together define then the so-called graph, which can be analyzed with graph theoretical metrics, such as network modularity or network efficiency, that allow insights into how information flow is organized within the brain. I'm not sure how familiar you are with these graph theoretical or with graph theory in general, but in brief, there are whole brain metrics that characterize the information flow within the whole brain, and there are region-specific or node-specific metrics that characterize how a specific brain region is embedded within the whole brain network. Finally, another basic point is that most previous work has primarily focused on intrinsic connectivity. Intrinsic connectivity is modeled on the basis of resting state fMRI data, so in the absence of any specific task instruction. People just lie in the scanner and have to look at the fixation cross. They are not instructed to do a mental task. But this is suggested to reflect fundamental organizational principles. In contrast, just very recently, an increasing number of network neuroscience studies focused also on task-related connectivity, allowing for insights into how the brain is connected during actual cognitive demands. Reviewing this field of research, it is relatively established that the major proportion of functional connectivity during tasks is similar to intrinsic connectivity. So representing some common truth, some common ground of interconnections, but when switching then from rest to task, an additional amount of connectivity is added. And these latter, task-induced add, can further be divided into task general adaptions and into task specific adaptions. So when you switch from rest to task, then a task general amount of connectivity changes come, and then some task specific are on the top added. Okay. So we have three types of connectivity: resting state connectivity, task general adaptions, and task specific adaptions. While in intrinsic connectivity, so this resting state connectivity presents the main portion, and it has also been shown that it has a strong genetic basis and it is highly replicable over time. So, what are some common findings? A common finding of structural network neuroscience studies on intelligence is that people with higher intelligence scores have an overall higher degree of connectivity, mostly captured by fractional anisotropy, the name of the measure. Fractional anisotropy is one of several measures that can be derived from diffusion tensor imaging and indexes the flow of water molecules within the brain. And this is used to model, to approximate where the structural white matter tracts are located in the brain. However, there are also a lot of studies that did not find this relation. Other studies suggest further that this relation may differ for men and women, namely a positive correlation in women and a negative correlation in men, and that intelligence-related differences are most prominent in white matter tracts linking frontal to parietal regions, so the equator and longitudinal fasciculi, linking frontal to occipital regions, tracts that link different frontal regions to each other, so the unquinato fasciculi, and finally connections between both hemispheres, the corpus callosum. The majority of previous functional connectivity studies of intelligence focused on resting state connectivity, as mentioned before, meaning that they aimed to capture these fundamental organizational properties. And what are different in these properties between higher and lower intelligence subjects. First studies in this regard investigated the intuitively plausible assumption whether the brains of more intelligent people are globally connected in a more efficient way, whereby higher efficiency in graph theoretical terms refers to shorter connections between two distant nodes. However, while the preliminary study of van den Heuvel supported this assumption, most recent work, inclusively my own work, could not replicate this finding. With respect to regional specific interconnections that relate to variations in intelligence, it's important to note that when reviewing this field of research, there is a very, very high degree of heterogeneity between different study findings. Small sample sizes, as mentioned by Adam before, the limited reliability of graph measures, and the high number of researchers' degrees of freedom in graph theoretical analysis may only be some of the reasons for this heterogeneity. For example, studies have not seldomly used different pre-processing strategies, different node parcellation schemes, and so forth. For this reason, I would like to point out here only 3 findings that have been reported across multiple studies. First, it seems that higher intelligence brains show higher functional connectivity within a set of frontoparietal brain regions. Second, this frontoparietal network seemed to be less connected with regions of the so-called default mode network, so that more intelligent subjects may have an increased anti-correlation, so no correlation, between brain regions that are typically activated during tasks and regions that are typically deactivated during cognitive tasks. And third, many studies that focused on region-specific connectivity, so on the embedding of brain regions within the whole network, often found that brain regions that have been linked to variations in attentional control result. This finding is schematically illustrated in blue and red lines in the figure you can see here. This should represent the anti-correlation between the task-activated and task-deactivated networks. And here you can see now the whole figure where I tried to subsume all these previous work about connectivity and intelligence, together with Olaf Spons from Bloomington University in Indiana. This is also published in the Cambridge Handbook of Intelligence, so you can look it up if you want to, or when it is no open access, just write me an email. I'm always happy to share because I don't like the paywall. Note further that all these graph theoretical investigations I talked so far about them focused on so-called static connectivity, meaning that connectivity was averaged over the whole duration of the resting state fMRI scan. Just very recently, a project of my research group started to investigate also connectivity dynamics, and other groups do this likewise. So temporal fluctuations or changes in connectivity during the resting state. In a first study, we used a sliding window approach to resting state fMRI data to investigate changes in intrinsic whole brain modularity, while modularity reflects how segregated or how integrated the brain network is as a whole. Just in brief, we observed a significant relation in our sample, namely that more intelligent subjects had less fluctuations in global modularity over time, which we interpreted as a sign of an intrinsically more stable network organization in higher intelligent persons. Post hoc analysis revealed that higher intelligent subjects had fewer states of very high segregation, so that the whole network becomes decoupled, and that this effect was primarily driven by the dorsal attention network. Notably, the sliding window approach that we used in this study has one major limitation. Namely, the temporal resolution which we can detect connectivity dynamics is still restricted by the length of the time window. Thus, we here developed a new machine learning based predictive modeling framework based on elastic net regression and eigenvector based feature generation that allows to test whether we actually can predict individual intelligence scores from connectivity dynamics from second to second. So we do not use the windows. We now use some mathematical operations that allow us to assess the dynamics time to time, so moment to moment. This framework is illustrated here, just for a short impression. Importantly, our new prediction framework can also be applied to all other individual differences variables. So if you are interested in some other variables, just let me know. And this framework overcomes the limitations from connectome-based predictive modeling, so CPM, introduced by Shen and Finn, which maybe you have heard about this before, but it has some limitations. But it is still the most popular approach, but I'm not so satisfied with this. Whenever you are interested, use our framework. Some advertisement. So coming back to our study, we did not investigate all connectivity time points, but applied a recently developed method to identify time points of strong whole brain connectivity, as well as moments of particularly low whole brain connectivity. Latent G factor was calculated on the basis of 12 cognitive tests, and this served as measure of intelligence. Of note, it has recently been shown that these specific moments of particularly high whole brain connectivity that represent only 5% of the whole resting state fMRI scan can construct or can predict the static connectivity matrix to 90%. And these specific moments of high co-fluctuation can also predict individuals' identity. So they seem to be something like a fingerprint. Could these specific states maybe predict intelligence? What do you think? Yeah.
Also, so many questions.
Yeah. Start.
Can I ask quickly? So you are saying this? It's a fingerprint of an individual, but in which way? Is it like a pattern in time of this emergence of those peaks, or is it like the percentage?
The pattern. Yeah.
Time pattern.
No, the spatial pattern. You only take these moments. And it is not where the moments are in time that is predictive, but the spatial pattern, so the connectivity pattern within these time points. So you take all these few time points, then combine it to a matrix, and then the pattern the spatial pattern within this matrix. There was a...
May I ask about the time scale of the changes, because there is no number.
Yeah, what use the microarray?
Okay. May I ask about the time scale of the changes?
Of course, of course. We have, unfortunately, fMRI, which is very, very slow, you know, so it is also delayed, the activity. And this is just a schematic illustration. We have 10 minutes resting state data, and when you then consider 5% of this, you have less. You have maybe less than a minute data, but this is only a schematic illustration, and here is not the range of milliseconds or so, like in EEG. We have the range of seconds.
Okay.
Because of...
I just want to know the time window sorry.
Yeah.
I'm asking because I want to know,
Yeah.
you know, at which time window the functional connectivity, you know, is higher than the tertiary.
Yes. Yeah.
1 second or tens of seconds or...
So this can be, for example, 10 seconds or some seconds, but not very fast. And also blurred by the hemodynamic response function, so we cannot clearly identify the time point in the brain with fMRI, but with some delay and approximation and some calculations and some uncertainty. Yes. Welcome, always welcome. Yes, so can we predict intelligence? What do you think?
Yes.
No, you are too optimistic. In contrast to our speculations and also your speculations, we observed that these 5% moments of especially high whole brain connectivity could not predict intelligence. But do we publish this now result? No, we should have done. No, we published it together with post hoc analysis, where we looked a little bit deeper into the data. So after some more deeper analysis, we found a way to show that it is indeed possible to predict intelligence from only 5% of this fMRI scan, but that these predictive moments must be temporally sufficient distinct from each other. We then extended this approach to test how much data is actually required to predict intelligence at all, and we found that it is already possible to achieve significant prediction with as few as 16 time frames. So as long as these are sufficiently separated in time. For a better impression, this is less than 1.5% of a 10-minute resting state fMRI scan, so around 3 seconds fMRI data. As long as these are not close in time, they need to be separated in time. So, to conclude, the results of this project suggest that although fundamental of a person's identity can be derived from few time frames of high connectivity, temporally more distributed information is necessary to extract information about individual variations in intelligence. This predictive information is, however, not restricted to specific connectivity states, like network-defining high co-fluctuation states, but rather reflected across the entire length of the brain connectivity time series.
Can I ask a question?
Yes.
So how about the rest of the data? So
You can throw it away.
So it doesn't predict anything?
Exactly.
Because you would expect that it's not only like these high connectivity moments, but also the diversity of
Natalia, wait a minute.
Yeah.
Yeah, so I'm just asking whether the rest of the data can also predict IQ or individual fingerprints, because only like 5% of the data would be very reductive.
Yeah, that is a good question. So in principle, you can throw it away. I would say that there is a lot of noise going on there, but this seemed to be sufficient to predict intelligence. And I would propose, but I'm leaning toward that these moments are also predictive for other types of. But it would be worse to transfer this approach to personality prediction, for example, to see whether these are the same moments or different moments in time, and what is going on there with the different. So, for intelligence, yeah, and it's also, yeah, it's a little bit. We also tested that it seemed a little bit arbitrary, which specific moments. So the only thing was to capture the temporal pattern to different time points. This was the only important thing. So, but as these has to be sufficiently separated in time, you cannot say you measure fMRI only 3 seconds. Because we need a representative sample, we need a time that allows to keep some representative samples of a longer scan. But with this representative samples, we can read a lot about a person. Okay, yeah.
The variability across subjects could be...
Wait.
Yeah, thank you. In some connectivity, dynamic connectivity analysis, people try to use variability across subjects as another parameter for evaluating the dynamics, because some people can have earlier or later peaks like these ones, and that could be another feature for the analysis. How is, I mean, the high IQ people have less or bigger variability in the peaks that you are showing the fMRI?
We had, so you mean you would then divide
the
this
standard deviation across subjects of this peaks. I mean, if this is some informative, or you...
Yes, and but this would require that I define intelligence groups, right?
Yeah.
Yeah.
Or abilities, or what? Yeah.
Because when I consider the standard deviation over subjects, I cannot predict with. Yeah, that might be worth. For example, whether high gifted individuals are closer together.
Yeah, exactly.
We have to do this.
That can change probably the regression analysis.
No, this is across the whole sample.
Yeah, exactly.
It can be different in different subgroups, but then we would have the problem of too few subjects. And this predictive modeling framework with machine learning techniques, for these are even 300 participants, in principle too less participants, too few data. But it could be, yes, it could be. Yeah. And this perfectly leads over to my next point that I wanted to stress, that it is important to mention, of course, that all of our studies that I presented today, we used open available fMRI data. So we did not collect the data on our own, but use multi-center project data from the Human Connecting Project, the NKI Rockland sample, and the Amsterdam Open MRI collection. That is open for use after successful application. So thanks for these data sharing initiatives. So now, all I said before was about intrinsic connectivity. You remember resting state connectivity, people lay in the scanner, look at the fixation cross or even not, and are not instructed to do anything. However, as mentioned before, in principle, connectivity can also be assessed during cognitive challenges. And wouldn't we assume that intelligence-related differences become also or even more present when intelligence behavior is actually in action? So in one of our further projects, we investigated differences between intrinsic connectivity measured during the resting state and task-related connectivity measured during different task states. More specifically, we were interested in brain network reconfiguration, operationalized as changes in connectivity between two specific cognitive states. We considered both the reconfiguration between resting state and various cognitive demands, and also differences between cognitive demands. So to this aim, we used data from 812 subjects of the Human Connectome project and replicated all of our analysis in 2 independent samples of the Amsterdam Open MRI collection. Again, intelligence was operationalized via the latent G factor calculated from 12 cognitive performance measures. So, what are the results? What do you think? Do more intelligent persons reconfigure their brain network more or even less when switching from rest to task? Or is there no differences at all?
Less.
More.
Less.
Less.
Okay, yeah, the majority seem to be right. Indeed, we found a significant effect.
Optimistic.
No, we always need also different opinions. So it's good to have different opinions. Diversity. Okay, no, I don't want to make any political statements here.
I think it can be predicted from neuronal efficiency hypothesis that less.
Exactly.
They should work more in a similar state to resting state. That's all.
Exactly. This perfectly links also to what you presented before.
So Rick Heyer is a genius. He predicted all the data 30 years before.
Maybe, yeah. I don't want to make any dangerous statements here. Okay. Indeed, we found a significant effect that replicated across all samples. Higher intelligence was linked to less brain network reconfiguration, so to higher similarity in connectivity between 2 different states. This was true when comparing resting state with different tasks, and also when comparing different tasks to each other. We also analyzed the contribution of different brain networks, as you can see here, and looked how different tasks differ in this effect. In sum, these results suggest that people with higher general intelligence may have an intrinsic brain network architecture that is per se closer to a network architecture as required by various cognitive demands. And this would mean that more intelligent people have to adapt their brain networks less, their connections, when external demands change. This might be very adaptive and can also be interpreted as a sign of being neurally more efficient. So, as you might have noticed, I started this talk with talking about correlations and continued with presenting you 2 studies that actually predicted individual intelligence scores by means of cross-validation and machine learning. In general, cross-validation means that one part of the sample, called the training set, is used to build or to train a model, a statistical model, while another part of the sample, called the test set, is subsequently used to evaluate the trained model. We can differentiate 3 types of cross-validation. In internal cross-validation, the whole sample is subdivided into, for example, 5 parts. Models are then trained on all but one part of the data and are then used to predict intelligence scores in the withheld part. In contrast, in log-box replication, the initial sample is only split once. Here, one part of the sample, for example 20%, is put in a locked box, so behind our desk, before any model development started. This sample is used only post hoc to test the final statistical model. And lastly, external cross-validation refers to cases in which models are built in one sample and are evaluated in a completely independent sample that differs in various properties such as demographics or data acquisition details. This represents the most difficult test of generalizability. Based on these considerations, a growing body of research evolved over the last few years and demonstrated that individual levels of cognitive ability can be predicted from brain characteristics such as functional connectivity. Most of this research was, however, conceptualized to reach the highest possible prediction performance, while insights into the neurobiological processes underlying the predictive concepts are limited or even completely lacking. Main limitations of these studies include the exclusive focus on general intelligence, the mere use of fMRI acquired during resting state, the neglect of potential nonlinear relationships with intelligence, and brain features that are not really interpretable. And finally, the lack of external cross-validation. Thus, in the next project, we try to overcome these limitations by using functional connectivity of 806 healthy adults assessed during resting state and during 7 different tasks to predict general intelligence, crystallized intelligence, and fluid intelligence separately with linear and with nonlinear machine learning models, to test the predictive performance of single brain networks, network combinations, and combinations of specific brain regions via simulated functional brain network lesioning, to compare prediction performance from connectivity of all brain regions proposed as relevant by established intelligence theories with random connections, to identify then a novel network of functional brain networks most critical for intelligence predictions, and finally to externally validate our findings in a completely independent sample containing additional 322 adults. We pre-registered our aims, our hypothesis, and all of our analysis plans to do not have these researchers' degrees of freedom and to have no opportunity to do p-hacking. And to ensure high robustness and generalizability of our results, we implemented all 3 possible cross-validation strategies. So first we split our sample and put one part of the sample in the log box under our desk for later replication. Then on the remaining 610 participants, we constructed our prediction models. And to ensure high robust parameters, we applied a 5-fold internal cross-validation scheme, so within the sample. And finally, as mentioned before, we used 2 completely independent samples for the most difficult test of generalizability, external replication. We developed,
very short question. Why did you don't use?
I repeated. It's okay. I repeated.
One leave-out validation. It seems.
Adam just asked why I do not use the leave one out cross-validation, LOO cross-validation scheme that is very frequently used in this field. I'm not satisfied with this, that it is so frequently used, because you can test it, and there are also a lot of paper out there that criticize this leave one out cross validation, and we also observed in our data or have observed this before, that it's very prone to overfitting. So it when you want to construct very robust models that can also be used to generalize on completely new data, it's better to use a 5-fold or a 10-fold cross-validation scheme where you put out 5% of the data and do this 5 times, or 10% of the data and do this 10 times, and not take out again and again only one subject. That often results in models that are very specific to specific samples. So I would recommend to not use this. Okay, but this is a good question. So we develop models here to predict general intelligence, fluid intelligence, and crystallized intelligence, and as all computed as latent G factors for multiple cognitive performance measures. And all these 3 intelligence components served as prediction targets, while functional connectivity from 8 different cognitive states were used as features. So let's directly come to the results. At first, we revealed that significant prediction of all 3 intelligence components was indeed possible, while general and crystallized intelligence could be better predicted than fluid intelligence. Second, as you clearly can see here, how well functional connectivity actually predicts intelligence critically depends on the cognitive state during which fMRI was obtained. Third, we developed a simulated brain network lesioning approach in which specific networks or specific combinations of networks were removed from the analysis. The main observation here was that although brain networks obviously differ in their predictive ability, the removal of complete large-scale brain systems, including all of their connections to all other regions, led to a remarkably small drop in overall predictive performance. Thus, the removal of large functional networks, or even all networks but one, could be well compensated by the remaining systems. Fourth, we questioned whether brain connections from brain regions proposed as basis of intelligence by established theories would maybe excel in their predictive ability and therefore serve some support for this theory. And here you can see the results. To keep it short, these theoretically selected brain connections provide better predictive performance than random connections. However, they predicted significantly worse than whole brain connectivity and do thus not serve support for a specific theory. Fifth and last, we applied advanced machine learning backmapping techniques that allow to derive importance scores for each brain connections with the aim of creating a new network that consists of the 1,000 brain connections most predictive of intelligence. And in line with our previous finding, this newly created intelligence network comprises connections that are widely distributed across the whole brain, not clustered into specific regions or network, and included a high number of very strong positive connections. So, what can we learn from all these findings about intelligence? At first, we found systematic variations in models predicting general, crystallized, and fluid intelligence, suggesting differences in their neural substrate. Second, we saw critical dependency of prediction performance depending on the cognitive state during which fMRI was assessed, which proposes that associations with individual differences in intelligence can be amplified by adequate task selection. third, we observed high compensation for the removal of brain-wide functional systems, which suggests redundancy in the neural characteristics that code a person's intelligence level. And this redundancy may have also an evolutionary advantage in protecting the neural code of intelligence in the human brain. Fourth, the widely distributed nature of the most 1,000 important brain connections that best predicted intelligence proposes general fluid and crystallized intelligence as properties that emerge from as global features from the entire brain rather than resulting from isolated brain regions or networks. And this speaks against the localization theories of intelligence. And of course, overall, our studies offers means and methods to the question of how prediction studies can be designed to maximize biologically meaningful insights into human brain functioning rather than only increase the prediction performance, but treat the prediction as a black box. Last but not least, I would provide you a brief impression of another ongoing project of my group. This project attempts to relate both major dimensions of connectivity to each other that I have introduced in the beginning. You might remember structural connectivity and functional connectivity. Here I often work with the metaphor of highways as structural routes and the actually present traffic as a metaphor for functional connectivity. Like in reality with traffic, also in the human brain it has been shown that not all structural routes are used similarly frequent. While some routes are nearly overcrowded, others are used only very rarely or not at all. And these unused routes are, of course, costly to keep, and because they require energy and time. Based on these considerations, one might expect that more intelligent subjects excel by an overall higher amount of coupling between structural and functional connectivity, as this might allow them to process task demands more efficient. In contrast, too high coupling could also restrict the free flow of information and potentially hinder the development of new ideas or novel strategies as required for logical and reasoning abilities. Or might it be that more structure-functioning coupling is advantageous in some brain regions but disadvantageous in other regions, and that an optimal adaptation of region-specific coupling to specific demands make more intelligent persons excel in cognitive abilities? What do you think?
Complex picture.
That's always right.
No meaningful interpretation.
No, we have always a meaningful interpretation, no. But it is a complex picture, yes. It is not the case that overall. But to answer these questions, we conducted 2 studies. And both have been published open access, so you don't have any paywalls. Specifically, we aim to explore at first whether structure-functioning coupling is associated with intelligence on a whole brain, so on a brain average level, whether coupling is associated with intelligence on a brain region-specific level, and whether this information about region-specific coupling enables the prediction of individual differences in intelligence. While in the first study we looked at intrinsic coupling, so uncoupling excess during the resting state, in the second study we considered the coupling during different cognitive demands. In both studies, we used open data of more than 500 subjects from the Human Connectome project and an independent sample from the AOMIC, from the Amsterdam Open MRI collection, for replication. Static functional connectivity were constructed on the basis of fMRI scans, while structural connectivity matrices were derived from diffusion tensor imaging. As the investigation of coupling represents a relatively new field of research, many approaches have been developed in the last years, and it is currently not that clear what best reflects the truth. From the purely statistical approach of just correlating both connectivity dimensions to rather complex biophysical models that consider the biological requirements but are computationally extremely costly, and we could not have been used for this large sample. In our studies, we therefore adopted a recent, somehow intermediate approach that is computationally feasible, even in larger samples, but still provides theoretically meaningful insights into intelligence neural processing. Specifically, we transformed individual structural connectivity matrices into so-called communication matrices using different communication measures. These communication measures model potential functional interactions on top of the structural connections and allow insights into different communication strategies. Also in this project, person-specific general intelligence scores were computed as latent G factor from 12 cognitive performance measures. So, as the first study has been published in Neuroimage, I will not go into much detail here, but some key findings at least. Those were, first, we observed that higher intelligence is significantly related to higher brain average coupling, but only when measured with path transitivity as communication measure. Second, there were significant differences in brain region-specific associations with intelligence, and different brain regions varied markedly in the communication measure that best captured their coupling, as illustrated in the figure here. So different communication strategies are used in different regions. Specifically, higher coupling in multimodal associative brain regions comprising also frontal parietal networks was beneficial for higher intelligence, while lower coupling seemed to be advantageous in unimodal areas like the visual or somato areas. Third, to account for these differences, we then developed a new cross-validation predictive modeling framework that allows to consider these regional differences in the communication strategies. And this,
with the coupling, you mean coupling between structural and functional connectivity, huh?
Exactly, between functional and structural connectivity. I just use the term coupling because the other function-structure coupling is so difficult. Okay, but always between both. Thank you. And this allows us then to predict individual intelligence scores. So when we consider and take care of all these, that different regions use different communication strategies. And importantly, we observed similar findings in the independent replication sample, which is nice. And also the prediction model constructed in the main sample also succeed to predict individual intelligence scores in the replication sample. So model constructed in one sample and then transferred, used to predict completely independent intelligence scores. And this suggests, on the one hand, that our results are stable, and on the other hand, that we succeed to create a model that can be transferred to different samples and maybe to the population. Concerning the second study of this project, we transferred this approach to task data and investigated the association between intelligence and structure-function coupling during 7 different cognitive demands. This study has been published in Nature Communications, and I will present only the main results in brief. First, we observed that in general, so on a group average level, the tasks differ in their amount of coupling, with highest coupling during resting state and lowest coupling during the emotion processing task. Second, concerning the relation to intelligence on a brain average level, intelligence was only significantly related to coupling in 1 out of 7 tasks, namely with higher coupling during the emotion processing task. And third, we also consider regional differences, and the overall, so we see that tasks differ in their amount of how they allow to predict intelligence scores, with cognitively demanding tasks allowing best prediction performance. Just in brief, I will shorten this. So to conclude, the second study of this project suggests the existence of an intrinsic coupling organization that enables fine-drawn adaptations that support efficient information processing by facilitating brain region-specific adjustment to external task demands. Specifically, more intelligent people might excel in best adapting their coupling strategies to specific requirements of the task. So, to briefly sum up, what can we take away from these research projects so far? At first, I presented you the results of our meta-analysis, revealing that previous research that aimed to localize intelligence in the structure or function of specific brain regions was characterized by enormous heterogeneity. Therefore, we concluded that a network perspective might be more appropriate when trying to understand how individual differences in intelligence are manifested within our brains. Also, I highlighted the limitations of explanatory work that looked for associations only in one and the same sample, and stressed that cross-validated predictive modeling approaches might be one mean to generate more robust research findings that also generalize across samples. Following these 2 new perspectives, I showed you a study in which we predicted intelligence from a widely distributed pattern of regional brain gray matter volume, as well as a study in which we developed a predictive modeling framework that allows us to predict individual intelligence scores from 16 time frames or 3 seconds fMRI resting state data. Next, we entered the topic of task-related connectivity and saw empirical evidence suggesting that more intelligent people have to reconfigure their brain networks less when switching from rest to task, and that significant prediction of individual intelligence scores requires a widely distributed brain network. Sufficient spatial distribution was here even more important than that the nodes were predicted by a specific intelligence theory before. Finally, we combined the 2 dimensions of brain structure and brain function to show that more intelligent people do not simply have lower or higher coupling across the whole brain, but that brain regions differ markedly in their preferred coupling strategy, and then the adaptation of this coupling strategy to specific task demands might enable more intelligent people to excel in their cognitive performance. So, what are the questions that my group is currently working on? At first, we are working on 2 different meta-analyses, as beyond cross-validation and replication, also systematic meta-analysis are one mean to enhance the robustness of research finding, and thus are urgently required. So as most EEG research on intelligence focused, or many studies are out there focusing on the P3 component and the mismatch negativity, we are actually conducting two different meta-analyses, one on the P300 and one on the mismatch negativity, assessing how across all work published before this might is linked to intelligence or even not. Concerning the first meta-analysis, the P300 meta-analysis, we have already results suggesting the existence of low but significant relationship with intelligence. The mismatch negativity meta-analysis is still in progress. And second, I started just some weeks ago a new research project focused on the neurobiological basis of giftedness, or more concrete on the question whether brain connectivity differs only quantitatively or also qualitatively in the brains of gifted individuals. So is giftedness more than having a high IQ? We will start with a meta-analysis on connectivity of giftedness, where we also will include a paper where Roberto Colom is noted as author. And then we will develop a network neuroscience model of giftedness. Third, I got funding just recently for a project which provides me now the opportunity to broaden my focus on the genetics of intelligence. Much in brief, we will start with identifying structural brain connections associated with intelligence with a new approach, then explore new genetic variations linked to intelligence, before we then test the mediation model, meaning if the influence from genes to intelligence is maybe mediated by structural connectivity that we will identify. But this is all work from different PhD projects, and before I close, I want to thank all these people involved in these projects, especially Jonas Thiele, the reconfiguration person, the new Lina Mitko for the new project with the genetics, and Joanna Popp, she is the main person in the coupling projects, and Maren Wehrheim, she is the temporal dynamic person. Paulina will be the giftedness person, and Tobias Noeth is my meta-analysis person, and all the collaborations partners, and for your patience and your attention. Thank you.
Thank you very much, Kirsten. We have 15 minutes or something like that for questions.
Something like that is good.
Because we need to have lunch.
So, question. Thank you. Regarding but it was fantastic. Thank you so much for your very good presentation today. The question is about these fantastic results about the whole network instead of specific networks. Does it mean that these specific networks that we are using broadly in many other topics in neuroscience are not really useful anymore, because the machine learning or this type of approaches will be taking more distributed or more distributed connections than before, because could be just an effect of the type of statistical approach we are using. I mean, parametrical approaches was taking these small networks because it was more appealing for that kind of approach. But machine learning, it needs like broader features, let's say that. So could be that the difference, or is just because the networks that we defined before were not well defined or not useful anymore? What's your
Yeah, thank you very much. It's an important question, and I think the latter might be true, because we do not need so many brain boxes. We have the problem that we have so many brain boxes. What we need is many participants. And in principle, the results of the machine learning approaches could also result in only one region or only one network. But they identified a whole network, or a distributed pattern of significant regions. And I would assume, or I suggest that many previous results, they are not meaningless. They were very important. For example, that it is a broad network. So the results of our meta-analysis in the beginning, the observation that there are different clusters in the brain. Without these former studies, we do not know. We would have not known. And it's also that not all regions are similar important. There are still networks, for example, the frontoparietal network, the attention networks, where more predictive features are clustered in, and other networks like the visual or the somatomotor network have less of these predictive features. But it is, in my opinion, it was a simplified, rather attractive opinion that we can link that intelligence is located in one region or two regions. It's unfortunately more complex.
And I have a second question. Okay? So the second question is because I'm coming from the more from the EEG and magnetoencephalography kind of analysis. So these fantastic results you found between the resting state and task, there is less differences in high IQ people. Could it be because the high IQ people are connecting the regions in phase synchrony and not in amplitude? Because in fMRI you see more amplitude connections, but could be that they are spending less energy. They are not like needing less activities, just they are connecting in phase. So they are not spending energy, so there is no need for blood flow. So that, I mean, yes. I don't know, I'm just trying to...
Yes, totally valid consideration, would be great. And when you found somewhere on the world a data set that has fMRI and EEG in the same participants, this is also concerns our study, right? We have a new study where we actually, together with Adam, where we look at network changes in during doing the Raven task, so doing really an intelligence test. And we have some results in EEG and we have some results in fMRI, but we could not link these together because these come from two samples, and we need a sample where both would have been assessed in the same participants at the same moment. And it is possible. You can do EEG in the scanner, but it is expensive, and at least to the best of my knowledge, there is no open data set that has also intelligence assessment. And this during a Raven test. Can we do this?
We can try that.
Okay, I would be happy to join. Yeah.
In the Human Connectome project, there is a number of MEG measurements, but they are not at the same time, I guess. So, but maybe and this is not so many for your analysis. But maybe it is the first step to try.
Yeah, that's right.
They have over 100, I guess, or something like this. People that were scanned with MEG and fMRI. but on different occasions.
Yeah. And also rest and tasks. So because I need to calculate the reconfiguration, huh? I need
You don't need to do those. You don't need MEG and MRI at the same time. You can
No.
have resting state and task for both in the same participant, but then at different times.
So they have they have MEG at resting state and at different tasks.
And back, I guess, to back.
At least then the reconfiguration is limited to rest and back, but at least.
Also 0 back and 2 back. They have 0 back, so it is just match the sample and 2 back.
Yeah, and the fMRI data has also 0 and 2.
Okay, so maybe it's
that's completely right. And in principle, our EEG pipeline can be also applied to MEG. Yeah.
Just an idea. My question is about the effect sizes for those machine learning predictions, because it's like 3% of variance, 7% of variance, and machine learning is a very powerful tool. So when you predict from noise, you have 3% of variance. For example, when we put a number of predictors from oscillatory EEG markers, we rarely end up with less than 30% of variance. So really?
That's crazy.
No, if each predictor predicts like, I don't know, 3-4% of variance, but they are independent, they together like 6 or 7 predictors can predict 30% of variance. This standard, this normal, typical situation in EEG data. So if you have one EEG data set and you compute different predictors that you know they are significant or even not significant, but they contribute to the overall R squared, and you have a number of such predictors, you always end up with a quarter of variance explained. It is genetics. A single gene doesn't predict much, but if you put a lot of them. So my question is, isn't it too small predictive power with such a powerful tool? If you can predict only 3% of variance, it is very problematic for such a powerful tool.
I have one back question first. What you mentioned before with the higher amounts of explained variant, is this cross-validated? Because when we only consider sample-specific variance, I can increase the prediction performance to 90%.
I think in cross-validation it's even more than 30%.
No.
I'm
because
speaking about real predictors, like, I don't know, coupling, power, or something like this. You build a ML model or simple regression model, you use all those predictors as an independent predictors of GF. And then you have 30% of variance. But when you take this predicted GF from this model and real GF, I think you mentioned this by cross-validation. But it was always one wave out, so maybe it was
I think
overestimated, but it was always more than 20% of variance. Definitely not 3. Let it be 10, 20, 30, it doesn't matter. It is much more than 3. So my question is whether should those effect sizes in prediction be larger than just a few percent of variance, because you are using a very powerful method. And whole brain information, so it's a plenty of information.
The critical question is, do these models you mentioned before transfer to independent data? Do they?
No.
Yeah, and this is a point. This is why machine learning models with cross-validation always have lower effect sizes, because the aim of them is to identify relationships that are so robust that they do not only hold truth in one sample where they were developed. When I only consider the training sample, we have effect sizes from going up to 0.8 or something like this with machine learning.
I mean the testing sample within one and the same data set. So, for example, those 20% of
yes.
testing sample, when you fitted the model on the remaining 80% of participants. So it is, I understand that predicting from one sample from the study done in Madrid, predicting the data on another sample, different people done in, I don't know, Berlin is tricky and can lead to small sample. But I understood that some of your results were within one sample, only cross-validated between the subsample were used to fit the model and the subsample used only to test the model. Maybe I misunderstood the figures.
Yeah, most of the results were so in nearly all study I presented today, we combined all three cross validations. So we first put the data, some data in the logbox, so that we have the chance to replicate in 20% of the Human Connectome project, but that we have not seen before, but still the Human Connectome project data. Then we internally cross-validate with 5-fold or so, which enhances the robustness a little bit. And maybe we get a correlation between predicted and observed score for 0.3 or 4. Then when we consider the logbox replication, it's a little bit smaller, and when we then consider the external validation, the effect sizes drop and result in 0.2. But I think 0.2 is more realistic. Although all reviewers often mention, explained variance is only 5%, but I think, okay, but it's more true. It captures more the truth, at least with our methodology. I'm happy when you can convince me of a difference.
No, I think your methodology is beautiful. Yeah, I really believe in independent replications of the models, but I was just curious that in some other areas of cognitive neuroscience intelligence research, single predictors can lead to 0.3 correlations, and when you take a number of such predictors, you end up with 20, 30, 40% of variance explained, but not on an independent sample.
Exactly, and so I would not trust. Sorry.
And you get the same effect sizes with very complicated models that take hundreds of predictors into account. So it is more my question. It is in Polish a proverb to take a big gun for a small bird. So whether it's not this case, the big machine learning gun is shoots a small bird.
Yeah, but I see. But my goal is not that I have the maximum explained variance. My goal is that my results are generalizable to the population. And this has the cost of smaller, much smaller effect sizes, but which are, in my opinion, much more, capture more the truth. Sorry. At least with our methodology. Maybe in future...
It is always a trade-off between effect size and robustness, but I think we should attend to both parameters. So replicating results robustly with very beautiful replicability, but that are 1% of variance are not that interesting, I think. But also getting one-shot result of explaining 100% of variance, which will be never replicated again, is also not interesting. We should end up something in between.
There is another question there.
Thank you. Well, first, thank you for the talk. It was really interesting. And my question is not going to be as professional as the ones before, but I just wanted, it was just a curious question, because you talked about the generability and stuff. I wanted to know if there has been some studies linking like the different strategies and the coupling in the brain with maybe different cultures, because I know like learning or being bred in a different place changes your reasoning, your language and stuff. And I wanted to know if there has been like studies linking different strategies that are not the ones that we use, but that are as useful as the ones that they like to reach the same intelligence.
Concerning really the coupling between structure and function, there are no studies out there because there are less than 5 studies at all. One, or maybe 6. One investigated the coupling with age, the relationship with age. One is coupling and some methodological papers, but it's very, very, I think there are maybe less than 5 that relate coupling to individual differences at all. So, but in principle, you are completely right that the same IQ score can be reached by different strategies, and these strategies may differ in culture, and there might be also research out there that considers this topic, but not with coupling, at least to the best of my knowledge.
Thank you.
If there is time. Thank you very much. It was, very informative talk.
Thank you.
And what I learned from your presentation is that maybe my alpha oscillation is slow, because in intelligence science I'm new. I just recently learned some material about intelligence from Roberto, but I know about network science, functional connectivity, but I couldn't follow all the information that you provided. I don't know if it is because, low capacity of my brain or low information processing speed. But so thank you very much. I keep my more specific question to the discussion session, but I have a naive question now. If we have all the information about, functional connectivity, we have functional fMRI, we have a structural fMRI, and it means that we have the coupling between these two. Based on your experience, can we predict intelligence of a person?
What do you mean with can we predict?
For example, we have an ideal machine learning method, and we have all the information, all the data, functional data, structural data, and it means that we have I learned that coupling between these two is important. So we have all of this data for one person, and we want to predict his intelligence. Is it possible based on your
It depends on the definition of possible. Because it is significantly possible, like in all of the studies, but with not such a high effect size, meaning that the error we would make when predicting the individual intelligence scores of a person, I would expect around, when we use all this information, around 7-8 IQ points. So we can above chance, we are better than chance, but we have some uncertainty.
Okay. You know what? Why I'm asking that? Because if we can predict based on these data with significant precision, I mean, when I say precision, for example, say the IQ of one person is 130, and you can predict it with this data with, say, 5 minus and 5 plus. It means that in this data, fMRI and MRI, you have enough information for prediction. So maybe I can say we don't need to go to a spectral analysis, and we don't need other data. But I'm skeptical that the functional and structural connectivity gives all the data that differentiate between the people. That's why I'm questioning it. But we can discuss later in more detail.
And my aim is also not to predict intelligence, because fMRI and MRI is expensive, and tests, paper pencil tests, are much cheaper, and we have 100%. So also, which is the criterion? Yes, we evaluate our models on the data from tests. So does the test better capture intelligence, or my machine learning models from fMRI? Can never be solved, this question, because then we would use an independent valid measure of intelligence. As long as our criteria is the test, so we cannot figure out this.
Okay, thank you.
Welcome.
Okay, are we done here now? Okay, so thank you very much again.
Thank you.